All right, this is day 4 of Unit 4. That means we're kind of sort of getting close to the test. This unit has 5 days. So today we're going to be looking at the graphs of polynomial functions. Here are some examples of what polynomials look like on the left, and on the right we have things that are not polynomials. So as you look at these graphs, you hopefully can maybe pick out some characteristics that all polynomials have um, that are different than things that are not polynomials. So if you look at these, you might notice, first of all, that polynomials are smooth. What smooth means is they don't have jagged parts that go to points or things like this that's called a cusp. Polynomials don't have those kind of things. They are smooth. Sometimes it looks like maybe this is getting to be a little bit jagged, but if you zoomed in on that and were able to make that just that small part of the graph bigger, it would actually be very, very smooth curve down there. So they are smooth and curvy. Another thing you might notice about polynomials is that they don't have jumps or holes or multiple pieces like these do over here. And in math, the way we would describe that is to say that they are continuous. No breaks, gaps, or jumps. Another thing that you might notice on the ends is that they continue to either increase or decrease. They never they never have behavior like this, and we'll talk more about what this behavior is, but this function essentially goes straight down. Polynomials do not do that. They're always sort of going outward, and probably the way that we would want to talk about this is through their domain. Their domain is all real numbers, or from negative infinity to positive infinity. Like this thing right here has a domain from 0 to infinity. As a more limited domain, polynomials do have an infinite domain. So those are the characteristics of polynomial functions if we look at their graphs. Today we're going to talk more in depth about 4 of the characteristics. Now, in some ways these are all reviews. We've talked about end behavior before. We've talked about mins and maxes before. We've talked about intercepts before. And we've talked about intervals of increase and decrease before. We're just going to talk about them through the lens of polynomials or in the context of polynomials. So first of all, let's see, in class we did a sorting activity. You're not going to do that on the computer, but what we did was we sorted some cards into functions with even degrees and functions with odd degrees. And we sorted them whether they had a positive leading coefficient or a negative leading coefficient. So if you sort them according to the function, you might notice that the graphs in each of those boxes have some things in common. For example, the even degree polynomials all have the two ends, the two end behavior are the same. Either they're both going up, if it's positive, or they're both going down if it is negative leading coefficient. So if it has an even degree, the two ends are doing the same thing. For odd degree, the two ends are the opposite. They're different. Either it starts low and it goes high. These ones have positive leading coefficient, or it starts low or starts high, like all of these ones start high on the left, and then on the right they go down, so they're decreasing overall. Now they might have a squiggle in between, like this one squiggles, but overall they start really high and go low, so they're decreasing. So overall, they increase or decrease if they have an odd degree. So we can use this pattern to help us answer questions and to help us think about the behavior of different polynomials, and it's kind of summarized in this chart. So if it's an even degree, the two ends are the same, either both up or both down. If it's positive, if it's odd degree, the two ends do different things. Now we can kind of use this chart in two ways. If we know the function, for example, if we were looking at this function, we would be able to tell, oh yeah, this has a negative coefficient and an odd degree. That means both ends go downward. So if you have the function itself, you can use the function to decide what the end behavior is. But we can also use this the other direction as well. If we have a picture of the graph and we know that on this side it's down and on this side it goes up, immediately I know that it has an odd degree and it has a positive leading coefficient. So, you know, it kind of can go both ways, and we'll use this idea to answer questions in both directions, and we'll use it for graphing a bit too next time. So let's just see if we can figure this out. Example 1, we have -1/2 x to the fourth plus a bunch of other terms, but if we want to determine the end behavior, really it just depends on this first term. This happens to be an even degree polynomial, and the leading coefficient of this is negative. So we have an even negative situation happening, and what that tells me, since it's even, either both ends are up or both ends are down, and since the leading coefficient is negative, that means both are down. So as x goes to positive infinity, this is talking about the right hand side of the graph, our function is going down, and as x goes to negative infinity, this is talking about the left side, the function is going down. So remember, when it talks about the x part of it, this is talking about left or right. That's in the x direction because it's the x. And the f of x part of it is talking about the up or down, and that's in the y direction. So here's what the function would look like if we graphed it. Now that would take some time to type into your calculator because it's quite a long function. And also it might be difficult to see on your graphing calculator unless you get really good at manipulating the zoom, because the default screen on your graphing calculator would just show you this. So it might be difficult to see. You'd have to adjust your zoom a lot in order to get a really good picture of the end behavior. But just looking at the function, we know the end behavior right away. So it's kind of like a shortcut. It's just a pattern. Okay, so let's see. F of x equals x to the third minus 6x squared plus 5x plus 12. Well, right away I can tell this function has an odd degree because it's degree 3. That's an odd number. And the leading coefficient is 1. That's a positive number. So because the function is odd, I know it's either going to be this or this, one or the other. Because it's odd and positive, positive tells me overall it's increasing, so it's going to be this one. So if we look at this end behavior, it says f of x approaches something as x goes to the right. Well, on the right hand side, this thing is going up. And f of x approaches something as x goes to negative infinity. This is talking about the left hand side. So on the left hand side, it's going to be going down. And here's a picture of the graph to sort of confirm that we were right. It goes down on the left, up on the right. Okay, we had 2 more to try in class. For this first one, this is odd and negative. Well, that means it's going to overall be decreasing like this on the ends. So it's going to go on the right down, and on the left it goes up towards infinity, really high. Second function is even degree. and this is a positive coefficient. So even positive means both ends are going to be pointing upward. And here's the graph to see if we did it right. On the right, down, on the left, up, and then on this part C, both ends up. Okay, so relative extrema, we've talked about these before, just a quick refresher. Polynomials tend to have relative extrema. Sometimes you'll also hear them called turning points because it's where the function turns around. So if we're looking for the minimum, relative min is a low point. Here it is right here at 3, -8. Relative maximum would be a high point. Here it is right here at 1, 0. Also, quick reminder of interval of increase or decrease. So if we read our function like a sentence, left to right, intervals of increase and decrease are portions of the domain. So we really want to focus on x values here. And if I think about left to right, first my function is increasing. So that would be from -infinity to 2. Again, we're focusing on those x values. And then it turns around and decreases between 2 and 4. That's right here, 2 to 4. And then once it reaches 4, it turns around and increases. So there's the interval of increase, -infinity to 2, 4 to infinity. And the interval of decrease is from 2 to 4. Okay, intercepts, reminder, easy peasy, right? We've got a bunch of x-intercepts, 1, 2, 3, 4. Our x-intercepts are -4, 0, -2, 0, 1, 0, and 3, 0. And we have just one y-intercept, that would be at 0, -1. Remember, they're typically for functions, there's only one y-intercept, and polynomials are functions, so just the one y-intercept. When you look at the x-intercepts of a polynomial, you can get some extra information by observing the behavior of the graph. So right here, we have what is called a terrace point. We've sort of briefly talked about these before. And on this other graph, we also have a terrace point right here. Terrace points are where it flattens out for a brief period of time, and they are sometimes also called inflection points. Terrace points, when you see a terrace point on the graph, it can give you some information about the multiplicity. It has, at that terrace point, for that corresponding factor, an odd multiplicity. And it has to be a degree higher than 1, so degree 3 or 5 or 7 or some higher number. So if we're thinking about just what's the least possible degree that it could have at that point, it would be degree 3. Sometimes the function just simply crosses from one side to the other. That would just be multiplicity 1. Let me rewrite that. Sorry. Don't want it red. And then another type we have are called tangent points. We've also said that this is the behavior when it touches the x-axis and turns around. So it's when you have a relative min or relative max on the x-axis as an intercept. So this is a tangent point, a tangent intercept. And this function has 2 of them. And the multiplicity has to be even here for these tangent points. So it could be 2, 4, 6, and if we're thinking about the lowest possible, it would be 2. So if I wanted to write the equation of either of these functions, or an equation for a function that looks very similar, I could write it using intercept form as x plus 4. That's right here. I would have multiplicity 3 on that. X plus 1, that would correspond to this intercept. And x minus 1 squared would correspond to this last tangent point of intercept. So this would be a potential function that would look like this behavior. And for this one, if I was writing it in intercept form, I would write x plus 2. That would be a third power because it's terracing. And we'd have an x minus 1 to the second power for this tangent point, and an x minus 5 to the second power for this one. Anyway, so watch out for that graph behavior. It can give you some additional information. Okay, so when we talk about the y-intercept, these are the same two functions, by the way. The y-intercept, if the function is in standard form, it can be really easy to find the y-intercept. It's the constant in the function. So in this case, it's 0, 64, and this point way up here is actually at y equals 64. Another way of thinking about it, or maybe the more formal way of thinking about it, is that the y-intercept happens when x is 0. So you could plug in 0 to each of these terms where the x is, and it would end up being just the negative 64. Or, sorry, it would be, it's a plus 64, but my circle is right on top of it. Of course. There we go, plus 64. Formally, it's putting 0 into the function for x. We're figuring out what the height of the function is if x is equal to 0. For polynomials, you can easily spot that as the constant at the end, which in this case is 64. In intercept form, it's a little bit trickier. You could literally just put 0 into the function. So this would be 0 minus 1, which is just negative 1, which is squared. This would be 0 plus 2, which is just 2, and that's raised to the third. And this would be 0 minus 5, which is just negative 5 squared. So the trick, if you're just trying to be fast and you notice the pattern happening, is you can just multiply sort of the ends because you're substituting 0 in for all of the x's. If we multiply that out, negative 1 over 25 times negative 1 squared times 2 to the third times negative 5 squared, you get negative 8. So if we plug in 0 for x, we get negative 8. And on the graph, that would be this point right here. Negative 8 is the y-intercept. So a little trickier in intercept form than standard form, but not too bad. Okay, I'm going to skip this for this little video. Least possible degree of the polynomial. Well, sometimes we're interested to know what is the lowest degree this polynomial could be. Well, if I'm looking at this first one, first of all, if I'm thinking about whether the degree is even or odd, I would just look at the two ends. If the two ends are the same, that means it's even. If the two ends are different, it's odd. So in this case, since the two ends are both pointing up, that's even. The fact that they're up and not down tells me that it has a positive leading coefficient. And the least possible degree, well, it has two intercepts, so it's got to be at least a degree 2 polynomial. It also starts by decreasing and then turns around and increases. That also tells me that it's degree 2. For the next function, well, the two ends are doing different things, so this is an odd polynomial. And overall, the trend is that it's decreasing, so that is negative. And the least possible degree this could be, well, I see 1, 2, 3 intercepts, so it's got to be at least degree 3. You can also think about the turns. It goes down, and then up, and then down, 3. Turns twice, so it's got to be degree 3. Last one. sorry. If we're thinking about this function for the degree, the two ends are doing different things. I've got one up high and one down low, so it's odd. And overall, it starts low and goes high, so overall increasing, so positive. And the least possible degree, well, I can only see two intercepts, but the behavior of the graph tells me that there are some multiplicities here. At this particular intercept, it's got to have at least a multiplicity of 2 because it's a tangent point. It's touching and turning around. And then this one over here, the behavior, that terrace, tells me that it has to be at least multiplicity of 3. So altogether, that tells me the lowest degree this thing could possibly be is 5. And I think that that is it. So on the homework, you're just going to be looking at some graphs and deciding based on either the equation or the picture if you think it is even or odd, positive leading coefficient or negative leading coefficient, and a few other questions about it. So if you have questions, please come in and let me know. Otherwise, that's it for today.